created a camera so fast it slows to a crawl the fastest moving thing in the universe, light.
The camera has a resolution of a trillionth of a frame per second. And so we can actually observe light as it goes through this scene.
A trillion frames per second?
Mm-hmm.
At that speed, a flash of light on a still life is transformed into a journey.
We'll see light coming in by its reflection off the floor.
Oh, wow.
As the light wave propagates, it'll hit the surface of the fruit and we'll see that light up. And then only after delay will you see the light hit the wall behind it, and only after another delay will you actually see the shadow behind it.
Wait, so the shadow doesn't appear instantaneously?
That's right, because the wall is farther away, it takes light longer time to reach it.
That's crazy.
So let me show you another example.
It may seem unremarkable at first, a soda bottle filled with water, but then a flash.
So you see the pulse of light enter in from the left?
This pulse is actually a packet of photons, particles of light.
And we can see its energy front sweeping across the bottle from left to right. And eventually the pulse will hit the cap and emit a bright flash.
Just think how fast it was traveling.
About 600 million miles per hour.
And how long did that event take in real life?
It took a billionth of a second for light to go from one end to the other.
So an event that took a nanosecond, it has been stretched to
about 20 seconds.
20 seconds. So that's a lot of stretching.
This is super slow motion.
Put another way, if you were to film that iconic apple with this camera and made a movie of the bullet entering the picture, going through the apple and out the other side,
it would take about a year to watch this entire movie.
This would take a year to watch?
That's right, yes.
Oh, I recognize this setup. So how exactly does this super fast camera slow things down?
We shine laser light inside the bottle. You can actually see the beam.
It looks like a continuous ray of light, but it's not.
The laser light emits a train of pulses, very fast.
The object is to capture just one of these pulses as it enters the bottle. To get this image, they actually have to take 500 separate pictures, each just photographing a narrow slice of the scene.
The camera looks at the scene through this mirror system, which rotates. And as the mirror moves, you record a different slice of the bottle at a time.
So in order to get a complete picture, you'd need 500 slices of it.
Exactly.
But how do you capture a single burst of light if you have to film it 500 times?
So what we do is, we don't shine just one laser pulse. We rely on the fact that the laser is shooting out pulses periodically in time, over and over again. For each laser pulse, the camera records one line of the scene at a time.
And the fact that each pulse looks the same as the last, that's why the finished movie looks like it's just one pulse.
Yes, we stitch it all together.
Taking it a step further,
so for example, if
when you combine the camera this fast with information processing,
by this wall,
it opens up some interesting possibilities. This camera over here can somehow see around the corner?
Precisely.
How does that work?
Well, what we do is we take our laser beam and we shine it onto another wall. That light bounces off the wall and scatters in all different directions.
Some of that light hits the mannequin. Because the camera is so fast, it can record the difference in time it takes for this path or this path, each of the billions of paths of bounced light that reach it.
So based on the fact that we know how fast light travels, we can build computer software to actually place all the light back where it came from on the object,
digitally reconstructing it.
After the reconstruction, it actually looks like an image of our object, like this.
Oh. And with more processing, a 3D image. It's similar to sonar, where an image is reconstructed from reflected sound waves.
It's similar, but in sonar, the object or the ground floor that you want to look at still has to be in the direct line of view of the camera. In this case, you no longer have that restriction.
So it has potential use for fire and rescue, and for automobiles to detect approaching vehicles around corners, or in medicine to visualize the inside of a person's body.